Talk of the day today on this side is about Accismus. Is that how are we saying that?
Accismus.
Accismus. I feel like there's an extra. Maybe you need 3 C's in there for that. And it's interesting because it's a it's an implementation of Percolator, which is a paper that Google had written on top of Accumulo, and it solves some particular problems that Accumulo and Bigtable have in general, and I'm glad Keith's going to be talking about that. So, thanks.
So if you can think of any new names for this project, I'll gladly take your suggestions. But I was looking around when I started working on this. I'm like, oh, I need a name. So I just started looking at A words I was looking for something unique, because I personally like things that when you Google them, they just automatically come to the top, even if they're not that well known yet. So this fits the bill as unique, but I don't think anyone knows how to pronounce it or what it is. I think it's a word that means it's an irony. It's like you pretend you don't want something even though you really do want it. And in this case, it's going to be transactions. It's like, I don't want transactions. My counts, they're within an order of magnitude of being correct. So I'm fine with that. So Percolator is an interesting paper that Google wrote. It's something that builds on top of Bigtable. And the problem they're trying to solve is this problem of incremental ingest. So the situation they lay out in the paper is they're indexing. So they have, I kind of made up these numbers from the paper. I think they may be bigger in the paper, I can't remember. But they have petabytes of data, and this is from crawling the web. And then they run a whole bunch of MapReduce jobs over this to produce their index that's used to service their search engine. And this takes, I think in the paper they said it takes 2 to 3 days to run these MapReduce jobs. So, and then every day they're constantly crawling the web, and they have terabytes of data coming in. So they have, new data coming in is 1/1000th of the size of the data that they have. But it's this constant new data stream. And so with their old system based on MapReduce, whenever a new web page was indexed, it would be 2 to 3 days before you could actually query it. So with Percolator, that went down to like 10 minutes. So Percolator is designed for incremental processing, so you can constantly keep up with this steady stream of small data coming in, like tens of terabytes, constantly updating. But what it's not designed for is you're not going to use Percolator to process a petabyte of data. And they have a nice little graph in the paper where it's like the ingest rate is going up, the size of the ingest, and the time it takes to process it with Percolator. And at some point there's a cliff where it just goes asymptotic. So you can't use Percolator to process your data, all of your data. And we'll talk about how you deal with that later. So Percolator, the way it works is it's built on top of Bigtable. It has its own API, and it offers cross-row transactions. So in the Bigtable data model, rows are not guaranteed to be on the same machine. So you can in the Bigtable paper, they talk about doing atomic changes to rows. You can do that. You can always make atomic changes to a row because you know it's going to be on one machine. And Accumulo kind of follows that. And I added something to Accumulo called conditional mutations and Accumulo 1.6 to support building Percolator. And I was going to talk about that today, but I don't think 30 minutes would have been enough to talk about conditional mutations and Percolator. But if you have time, somebody wrote a pretty good blog post about conditional mutations. I found that. And also there's a really good example about conditional mutations that shows how you can build a reservation system in Accumulo. Like if you wanted to reserve seats on an airline or something like that, and you want to do it atomically and make sure that 2 people don't get reserved the same seat or something like that. But so Percolator relies on conditional mutations and to offer cross-row transactions. It offers snapshot isolation, which, if you're familiar with different isolation levels in databases, serializable is the best. Snapshot isolation is a little bit better. You read committed data, but you can have something they talk about in the paper called write skew. And usually it's not a problem, but if your transaction, if the transaction makes computations based on data it doesn't write, then you have to think about that. But usually that's not the case. So the Percolator API, it exposes the big table data model, the row, column family, column qualifier. It exposes everything but the timestamp. The timestamp is used by Percolator to keep its own versions. And once you have these transactions, it's like, okay, what's the processing model? What do you do with them? The processing model in Percolator is that they have these things called observers. And on every node in the cluster, you run a worker process. And the worker process will run hundreds of threads that execute these observers, which are basically user-provided code that execute transactions. So if you're not familiar with transactions, and this is to get everyone's kind of brain going and make you think about what can happen and what Percolator is going to take care of for you that you don't have to worry about. So this is a simple transaction. I'm going to talk about a few transactions that deal with banking, so like transferring money between people's accounts. So this is a transaction to initialize 3 bank accounts for Bob, Joe, and Sue. So what could possibly go wrong? Anyone want to offer any suggestions? Let me set the stage. So Bob, Joe, and Sue, those are 3 different rows, and then balance is the column. Those 3 rows could be stored on 3 different machines, and the transaction could be running on another machine. So there could be 4 machines involved here. Some of the things that could go wrong is one of the machines could go down. Someone else could try to run a transaction that's going to modify Bob. So you're trying to check, oh, if Bob's not initialized, then I'll initialize it. You could modify 2 of the rows, and then the machine that's executing the transaction dies, so then you don't get to modify the other 2. So these are all the things that the system's going to take care of for you, and you don't have to worry about. Now this is showing, so once we have things initialized, this is showing a transaction that's going to transfer money between 2 accounts. So in this case, we have 2 threads running on 2 different nodes. They're going to read 2 rows that could be on 2 different machines. So there could be four nodes involved here. Now in the Percolator data model with snapshot isolation, if transaction 2, as long as if it commits before transaction 3 starts, then transaction 3 will see its changes. If transaction 2 does not commit before transaction 3 starts, then it will not see the changes. But what you get here is you get the reliance that you'll never end up with like adding $7 to Joe's account and not deducting $7 from Bob's account, or vice versa. So one of the unit tests that I've written so I have a prototype on GitHub for this, and it's pretty far along. And one of the unit tests that I've written is, I call it the Stochastic Bank, because you're never quite sure what your balance is, but you can make probabilistic assertions about it. But what the test does, and it's kind of cool to see it work, is it creates like, say, 1,000 bank accounts. And then it initializes each one of them to have $1,000. And then it starts up a lot of threads that just randomly pick 2 bank accounts and transfer money between them. So while these threads are running, there will be another thread that will just scan all of the bank accounts. And what's cool about this is the sum always comes out to n times 1,000, even though there's all this chaos going on with randomly transferring money around. Well, as long as Accismus is working, that's the case. So the test is pretty good at finding problems. But that really shows the power of snapshot isolation. I mean, when you can scale this up to a cluster size, you can actually use a MapReduce job to read an Accismus table and get a consistent snapshot of it at a point in time across an entire cluster. And that's actually really cool, because there can be transactions running, but you're going to see how your data looks from the MapReduce's job at a cluster level, and it's going to be consistent. So one of the things I'm going to walk through is a phrase count example that I've written. I've spent a lot of time working on this, because when you read the Google paper, they tell you, like, well, this is how we implemented Percolator. But then you're kind of scratching your head and like, well, how would I use this? And this example, I think, for the most part, kind of shows a pretty basic, easy to use example that shows how you would actually use Percolator. And what the example does is you take a set of documents and you dedupe them. So if two documents, so if you had two web pages that had the exact same content, you would only compute the phrase counts for one of those, one copy of those, not both. So you dedupe them, and after you've deduped them, you compute the phrase counts. This could be done with two MapReduce jobs. It'd be pretty simple. One MapReduce job to dedupe, and then another MapReduce job to count the phrases. Now, one thing I haven't done yet is I haven't done MapReduce. This is something that I said I would talk about later, because you only want to use Percolator for incremental processing. So, and I haven't implemented this yet, but what you would want to do is you would want to run MapReduce jobs to generate your initial Percolator table. And then you would use Percolator to continually process incoming data. So a Percolator application, or kind of the workflow when you're using Percolators, you're going to have MapReduce for your new data, and then you're going to run something called load transactions to continually process incoming data. And then you're going to set up observers, which are run by the Percolator worker processes, to continually transform data in a transactional way. And then you're going to have export transactions, which take the data from Percolator and export it to somewhere where you can query it. So the phrase count example kind of works like this. So a load transaction starts up, and so an input's going to be a document that says, my dog is very nice. It comes from foo.com/a. So that's one load transaction. It loads that. And then another load transaction runs, and from a different source, we get the exact same document. So it goes there, and then a third load transaction runs, and we have a different document from a different source. So now the documents are loaded, but we've got to get our phrase counts. So I've set up an observer in the system that says, when you see a certain modification made, execute another transaction. So the observer runs, and it indexes two phrases in that document and updates the counts. So that's that's a transaction. And then another transaction runs. And you can see that, so now we have two documents updating the count for one of the phrases. And this is all done in a transactional way. If those transactions had run at the same time, had failed, any of the bad things that can happen, you're still going to end up with accurate counts, and you're not going to have to worry about it. Now, if you run another load transaction, and you're like, so in the Google example, so you're crawling the web, and the content for foo.com/c has changed. And just because I don't have much space, I made it change to an existing document. So now we have three documents that have the same content. So this other document is no longer referenced by any location. So my observer sees that and it decrements the counts. So this is where you can really see the power of Percolator, because that's the type of thing that's really hard to get right, that incremental processing where it's like, oh, reference count went to 0. I'm just going to decrement the counts. Your counts are going to be accurate. You don't have to worry about it. You're not going to end up with like -1. As long as you write your code correctly and the system's working correctly, the counts are going to be right. So this is the schema for that example. And now the current implementation just stores all the data in one table. So what I've been doing since I've been storing everything in one table is I just put prefixes. So I have a prefix for the URI, and then for the document, I'll have the document and then stored by its SHA-1 hash. And then I'll have the phrases, and then I'll have the count associated with the phrase. So some of the things that are interesting is I'm just keeping track of my state. So like I'll keep the track of so you see like I have doc hash doc reference count. So I'll keep track of the reference count for each document. That's how many sources, like when I had the 2 URIs that referenced that one document, that's just a reference count that I can keep and I can update transactionally. And I also I was thinking about I had to keep the status, like whether I've indexed it or not. Because if the reference count drops to 0, I need to keep track of whether or not I've indexed it. Because if the reference count drops to 0 and I haven't indexed it, then I don't want to unindex it. I don't want to decrement the counts. Because it could be possible that you load something, reference it, and then another load transaction dereferences it, but it was actually never, the phrase counts were actually never updated by an observer. So when I first started looking at this paper, and I was thinking about how do you use this, I think they had one sentence in the paper that mentioned, maybe 1 or 2 sentences that mentioned export transactions. And I was like, what is that? How does that work? That's one of the things I had to kind of puzzle through. But the way Percolator is designed, it's designed for throughput. The transactions are not, it's not designed for OLTP. You don't want to use it for like online, like banking. You don't want to use it for things that have to be responsive. And the reason behind this is because the way Percolator recovers from failed transactions. It does a lazy recovery. It's just like, oh, if a transaction modified 50 things and then it fails in the middle, those 50 things will be left as they are until someone comes along and tries to read them. And then when someone comes along and tries to read them, then it'll start doing recovery. And that could take a while. So if you're trying to do OLTP and someone's at an ATM, you don't want it to start doing recovery when they're doing their ATM transaction. So those types of systems are much more aggressive about recovery, but Percolator is like, because it's designed for throughput. It's not designed for responsiveness. So, but the export transactions are kind of scary, because once you start working with Percolator, it's this nice environment with transactions. It's very sane. But when you start to leave Percolator and try to get data out of it, you're losing that sanity of, and it's like all these things can go wrong. So your export transaction could die in the middle. So you could be exporting to Accumulo and things could just die in the middle. You could have 2 things concurrently trying to export something. Or you could have out of order arrival for your exports. So I've kind of come up with one way for dealing with this, and this is in the example, in the phrase count example that I've created. So there's kind of 3, I don't know, if you could think of this as a recipe, there's kind of 3 things you need to do. So one thing is if you're going to export something, you need to commit it before you attempt to export it. So only export committed data. So that would be kind of called an intent log. So you don't do something until you've serialized it or you've persisted it to disk. You persist to disk the action you want to take before you try to take the action. you want your export transactions to be idempotent. They've got to be able to execute multiple times, and that's got to be okay. And I'm using a committed sequence number. So that's for ordering things as they go out. Now that works really nice with Accumulo, because with the Accumulo timestamps, if you export data, and you have this situation I have up here on the slide where, say you have an export transaction that starts to run, and then it goes to sleep. Like the machine's swapping, the Java garbage collector kicks in, it goes to sleep for like, I don't know, a few minutes. So the process is there, it's idle, but it's in the middle of doing the work. And then the process wakes up and starts doing the work again. But while it was doing that, new data has come in, and someone has already exported the newer data. So this thing that's been asleep for a while wakes up and exports the older data. So in that case, the sequence number, it'll export it with the old sequence number. Now, if you use this sequence number as the timestamp in Accumulo, then the data will sort properly, such that the old data will just sort automatically behind the new data. So that kind of works nicely, and that's what I have in the example right now. So the example will export to an Accumulo table, and the purpose of doing that is so you can query it without any delays for recovering transactions. But the sequence number will help order data so that the newest data will always sort first. And this is how, and these are some extra things I've added to the schema for exporting. So like I said, if the phrase counts update, like they could update like 5 or 6 times, but I'll keep track of what I'm trying to export independently of what the current phrase count is. And then the export transaction, after it successfully runs, it'll actually notify itself again if there's new data, and it'll commit that and then rerun another export. So I didn't have enough room to put it all in one slide, but the total schema, like I'll have a count. Actually, that should be sum. But I'll have a stat sum for the phrase. And then I'll have an export sum. And I'll keep track of those separately for each phrase. So it's like the current sum for a phrase, and then there's the one I'm attempting to export. And I don't think I mentioned this earlier. The export check column is what triggers an observer. So whenever a new phrase comes in and it gets updated, I'll actually set that special column, and that triggers the observer to run and look at it and try to do the export. So actually this slide, I prepared these slides about a week ago, and at the time I did not have, in the phrase count example, handling for high cardinality phrases. So if you had a phrase that occurs in every document, then you're going to get contention with your transaction. So, I don't know, like if you were indexing the Apache website, like you would see the phrase, the Apache Software Foundation, in almost every web page. And if you're running transactions and they're all trying to update that one count, they're all going to hit that. The transactions are going to collide. And, so, if you have 20 transactions, they all try to update the same count at the same time. One of them is going to succeed, and 19 are going to have to fail and roll back. So to deal with this, there's something in the Percolator paper that they mentioned called weak notifications, where you can set a notification, and that can cause multiple observers to run, but it doesn't matter if they run concurrently. Multiple can commit. So normal notifications in the Percolator paper, only one thing can commit. And there's actually another problem with the example that I haven't quite worked out in the example, but memory exhaustion. So the Percolator model, you have, on each worker process, you'll probably run like 20 to 100 threads. You'll run lots of threads to get a lot of throughput with your transactions. But if one of my transactions tried to load an enormous document, or actually if like 3 or 4 threads try to do that, then you could blow out memory on the process. So, but I think that's just a way of, I just need to handle that. I'm not sure if there's anything I can do in Percolator to handle that. It's more of the application's going to have to do something to handle that, to split up large documents or something like that. So this is just showing the weak notification example, and this is implemented in the example. And what I do, so when I'm indexing a document, normally I would go straight to the phrase and update its count. If I detect that it's a high cardinality phrase, then I'll just pick a random, column under the phrase and just set that. And then I'll set this weak notification. And then an observer will come along and it will see all the random columns and sum them up and update the main count. So basically what happens is for high cardinality phrases, you'll break updating it into 2 transactions. It's more, you wouldn't want to do that for every phrase, for the low cardinality phrases, because more transactions, it's just more, it's unnecessary work. But for the high cardinality phrases, you have to do it, or you're going to have a lot of work just rolling back transactions. Yeah.
Are you automatically determining the high cardinality, or is that something you just need to know about the data?
So in the example, what I did was I used local information. And I'm not sure if it's best, but what I did is say a document had like 50 phrases in it, I just go through and I know the count, like I've read the count for all those phrases. So I'll calculate the average and standard deviation, and any count that's 1 standard deviation above, I'll just say, oh, that's high cardinality. I think in a real application, you'd want to do something better. You'd want to get more global knowledge, which I think you could calculate in Percolator. It would make the example more complicated. So I went with this simple, look for anything that's 1 standard deviation above and say, oh, that's high cardinality. And this was something else I was thinking of for handling high cardinality. And this might be good for doing the global information. If you wanted to calculate the total number of phrases in the system or something like that, I was thinking of having like a tree of transactions where you start off at a really low level with lots of nodes, and then you set things there, and then you have observers that kind of percolate things up the tree, so that the goal here is to avoid contention. So that ideally you don't want transactions trying to update the same thing too often. You want that to happen as infrequently as possible. But I don't know. This is just something I was thinking of when I was working through this example. I'm not sure how well it would work. So I've been talking about the example. I'm going to start talking about the implementation of Percolator. And this is stuff that's in the paper. I'm going to cover some things also that they didn't talk about in the paper. I'm kind of curious how they did it. But one of the things they talk about in the paper is this timestamp oracle. So when you run Percolator, it runs on the same nodes as Accumulo. You have all these worker processes running on the same nodes as Accumulo. And you also run something called a timestamp oracle. And you run just one of these guys. And the timestamp oracle just gives out timestamps to the worker nodes. But they're not real timestamps. They're just one-up counters. And it's just used for logically ordering transactions. And even though it is a single node, it's such a simple service that it can handle, I think in the Google paper, that they didn't have a problem scaling it. So, because it's just doing a really simple task. But when a transaction executes, it gets a timestamp when it starts, a logical timestamp. And then when it commits, it gets another logical timestamp. And those logically order events to give you snapshot isolation, to ensure that you only read committed data. So the implementation uses two-phase commit on the cluster. And the transaction, the two-phase commit transaction, can actually run on any node in the cluster. And there's no centralized service except for the timestamp oracle, which is really quick. And with the timestamp oracle, they talk about it in the paper. They talk about you want to batch and I'm doing this in the implementation, you want to batch requests to it. So if you had 100 threads running on a worker, and they all request a timestamp at around the same time, you'll send one request and get back 100 timestamps and kind of dish those out. So that really cuts down on the RPC. But walking through the two-phase commit, so Percolator will, if you're writing to, say, 20 row columns, it'll just pick one of those as the primary. And then it will try to lock that column. So it'll write some special data into Accumulo using a conditional mutation to lock the column. And then if it successfully locks the primary column, it'll use conditional mutations to lock all of the other columns, row columns in Accumulo. Once it gets all the row columns locked, that prevents any transaction that started after your transaction from reading the data. They'll block, they'll wait. And then it can, after it has everything locked, it can kind of commit the primary column, and then it can commit all the other columns. So the way lazy rollback works is it uses this primary column. So if this transaction fails, all the row columns point to the primary column. I'm going to show that later. But if that serves as the authoritative source for rolling back or rolling forward the transaction. Yeah, so that's what I was just talking about. So if a transaction dies before you've done the first two steps, you'll roll back. If a transaction dies after you've done the first two steps, then another transaction will roll it forward. So if you read the Percolator paper, they talk about, for every row column, Percolator has its own set of columns. And I think in the Percolator paper, they just appended these to the column qualifier. I couldn't do that in Accumulo because that would have resulted in appending something to column visibility, and I can't just append random things to the column visibility expression. So what I did is I had to get something, I kind of needed that same sort order that they're using, so I appended something to the beginning of the timestamp. So I took the first 4 bits of the Accumulo timestamp and I turned that into this Percolator column. But so that we have this like write and data, those are the Percolator column types. So I'm going to walk through how Percolator transfers like $7 between these two accounts. So it starts off, so I'm going to transfer, I guess, I'm going to take $7 from Bob, and I'm going to give $7 to Joe. So the transaction starts off, and it locks Bob, the Bob balance column, and it also says Bob balance is the primary column in the transaction. The transaction start timestamp is 3. That came from the timestamp oracle. And then the second part is it tries to lock all other row columns involved in the transaction. So it locks the Joe balance column. And you see that the Joe balance column, it points to the Bob balance column as the primary column in the transaction. And you also see that it's written some new data. So it's written 93 and 107. Now, if another transaction were to come along and try to read right now, depending on when that transaction started, okay, how much longer do I have? 4 minutes. Okay, depending on when that transaction started, it would either see 100, 100, or it would see 93, 107. It would never see anything else because of the way that the timestamps work with the timestamp oracle. So, yeah. So when the transaction commits, it deletes the lock column, and then it writes a pointer to 93. So you have the write 6, which points to 393. And then it deletes the other column, and now the transaction's finished. So if the transaction had failed at this point, you would be able to look at the primary column, see it was committed, and roll the transaction forward. And so let me try to finish this up really quickly. So one thing that was not mentioned at all in the Percolator paper was garbage collection. So as these transactions run, they just leave a paper trail behind them of everything they've ever done. And that's got to be cleaned up somehow. I don't know how you could run and just leave that behind forever. So I did this with an iterator, an Accumulo, that just deletes, right now it's deleting it only keeps 3 versions around. So I need to do something better. I need to probably store something in Zookeeper that gives me some information on what the oldest running transaction is and use that for garbage collection. But this is still safe, what I'm doing. Because what I do is when I delete things, I write this truncation information. So if you try to read past what the garbage collector has deleted, it'll throw an exception and then it'll just retry the transaction. Because you can't really, I had to write this special information with garbage collection because you can't tell the difference between data being garbage collection and there not being data before a certain point in time. And I have another iterator that I wrote for reading data from Percolator. So when a transaction runs, it has a certain timestamp, and it only reads data that's been committed before that timestamp. So I could bring all the data back, all the different versions back to the client side, and try to figure out what I should actually do. But I have an iterator that does that. It does all the filtering on the server side to give me back all the committed data. And it will also detect if I'm trying to read past garbage collection. So one of the things I'd really like people to look at is the API. I've been trying to make the API very minimal, kind of is something I've been doing lately, and then build a type API on top of that that can support things like integers, strings, longs. But anyway, yeah, if you have some time, I'd really appreciate anyone who wants to take a look at the Accismus API and give me feedback. And I have a long list of things that I would like to do. Let's see. So one of the things that would be nice would be able to run on Yarn. So you have to start up all these worker processes, and it would be nice to be able to use Yarn just to start those up. I need to do the MapReduce code where you can actually write out an Accismus file that can be bulk imported into Accumulo. Need to improve garbage collection. And I want to write a test similar to the Accumulo's scale test where I can test Accismus at scale. So I can basically generate some random data, MapReduce it, and then take that same data and ingest it into Accismus and verify that the results are the same. And you can find the code on GitHub. And I'm hoping to have an alpha, a feature complete alpha done in a month or two. So, but please take a look at the code if you have time. And if you're interested in collaborating, let me know. Thanks.